We now know that light is considered to be both a particle and a wave. But exactly how does light travel? Well, we simply say that light travels in straight lines. Because of the fact that light travels in straight lines, we can observe many different phenomena. One such phenomena is a shadow. A shadow is simply light continuing after it has passed through an opaque object. It is because light travels in a straight line that we can see a sharp shadow. What is an eclipse? An eclipse is a shadow cast either on the Earth's surface or on the Moon's surface. There are two types of eclipses, solar and lunar. A solar eclipse occurs when the Moon is exactly between our view here on the Earth and the Sun. A lunar eclipse is when the Earth is in between the Sun and the Moon. Let's take a look at this clip to learn more about the two types of eclipses and when they can occur.
We have set up this cool little solar system right here in Studio 57. Now, we all know that the Earth revolves around the Sun and that the Moon revolves around the Earth. But at least twice a year, they fall into alignment, and you get some kind of eclipse, be it a lunar eclipse or a solar eclipse. The total solar eclipse, well, that's the big show, and that's where the Moon completely blocks out the Sun. And it's only possible because even though the Sun is 400 times larger than this little Moon, the Moon is 400 times closer to the Earth. And as a result, from our perspective, when we look up at the sky, the Sun and the Moon, they look like they're about the same size. And when that Sun hits the Moon and casts its shadow on the Earth, you get a couple of different types of shadows. Number one, most of you are going to see a very large penumbra. That's a partial shadow where you still see a portion of the Sun. But a select few of you are going to get to see the umbra. And that's nature's big event. That's where the Moon completely blocks out the Sun. It's called totality. And the area where it hits on the Earth is known as the path of totality. And on Monday, it goes from Oregon to South Carolina.
Next, we will learn about pinhole cameras. A pinhole camera is a primitive device, probably the very first camera that was used to capture images. You can make one with photographic film or without. If it doesn't have photographic film, then technically it is just a pinhole viewer. So here is a picture of a pinhole camera. How does it work? Well, a key principle of it is that light travels in straight lines. You have here a box with a little tiny hole in it, the size of a pin. That's why it's called a pinhole camera or pinhole viewer. And light enters in through that hole via a straight line. Because light travels in straight lines, then your image is inverted. It is upside down, both vertically and laterally inverted. So it appears sideways inverted as well. So now let's look at some examples of calculating distances using a pinhole camera. Okay, so here we have our pinhole camera formula. and it is basic geometry. It has to do with the theory of similar triangles. What are similar triangles? It are triangles that are the same but just of different sizes. So basically, this little triangle here is the same as that triangle, but it is just enlarged and flipped upside down. Why is it that way? Well, it's because light travels in straight lines. Remember, that's why the image is inverted. So here, what do OH, OD, ID, and IH stand for? OH stands for the object height. OD is the object distance. ID is the image distance, and IH is the image height. So what is our formula here saying? It is saying basically that the ratio of the object height to the image height is the same ratio as the object distance to the image distance. And that is a direct result of the geometry of similar triangles. Think about it this way. You're just taking one triangle and scaling it up. You're not making it stretch out in one way or the other. It is the same proportions. So it's the same ratio. So now let's do an example using the pinhole camera formula to calculate an actual height of a building. So let's say we have a building that is 500 meters away from a person who is viewing it using a pinhole camera. The image is 3 centimeters tall when they measure it using their pinhole camera, and it is located 25 centimeters from the pinhole, which they know because they have made their pinhole camera with a length of 25 centimeters. So using this information, how tall is the building? So here we have our little diagram. We can identify our information. The object distance is 500 meters. That's how far away the building is from the person. The image height is 3 centimeters, right? Okay, that's the tallness, the height of the image. And the image distance is 25 centimeters because we know it is located 25 centimeters away from the pinhole. What is the object height? So our formula is object distance over image distance is equal to object height over image height. We substitute our values and then we rearrange to get the object height. So when we rearrange, the object height will be 500 meters multiplied by 3 centimeters divided by 25 centimeters. And you might have noticed that I did not convert these centimeters to meters like I did previously with Young's double slit formula. Why is that the case? Well, as we see here, it is not necessary because the centimeters cancel out and we're left with 60 meters. So here, the height of the building is 60 meters. You might also notice that this formula is not the exact same one that I mentioned a little while ago. And really, it doesn't matter. You could have the object height and image height on this side, the object distance and the image distance on that side. It doesn't really matter, so long as they are corresponding. And what I mean by that is, you have object with object, you have distance with distance, height with height, things like that. It's all a ratio, okay?